Hey guys, in this next video we're going to talk a little bit more about the different function families and the different characteristics of those function families, and we're going to learn how to group functions based on number one, their shape, and number two, what the equations look like. So this video right here is going to be a little bit more interactive on your part and less so on mine. What I'm going to do is I'm going to have you grab those 20 graphs that you received in class, okay, and that some of you cut out, and then also your graphing calculator, and you're going to go through this notes packet here for 4.4 day 2, and you are going to match each of those graphs with their equations using your graphing calculator. Okay, so right now you're going to look at the first page here, and you have three different linear functions on this page, and you're going to go through on your calculator one by one, type in each of these functions on your calculator, and then find the correct graph, okay, based on what your calculator gives you, and then you're just going to tape that graph above that equation. Okay, so you're going to do that for all 20 of these equations here, and then so you're going to pause the video to do that, okay, and once that's all finished, you're going to click play back on this video, and then we're going to just run through really quickly what you should have come up with. Okay, so most of this notes taking here is going to be sort of on your own, and again, once you've finished with all of your graphs, you're going to go ahead and you're going to click play to check your answers. It might be beneficial to just set out your graphs without taping them, just to make sure you get it right, and then once you've checked to see that you get the same thing that I have in the video, then actually paste your graphs on the paper. Okay, so right now I want you to hit pause, go through and match all the graphs to their equations, and once you've done all 20 of those, click play, and we'll go ahead and we'll go through the answers. Okay guys, so now that you've sorted all these graphs, let's take a look and see if your answers match what I have. So for the first page, you should have these three different graphs. So the equation f of x equals x should match with graph H. The equation f of x equals negative 2/3 x plus 5 should match with graph G. And then finally, f of x equals 2 goes with graph C. So if you didn't get those, be sure you go back through and resort those. And now let's go ahead and talk about this first group of function families. This is what we refer to as the linear functions. So one reason they're called the linear functions is because when you graph them, you get a line every single time. Okay, notice the first two graphs you get diagonal lines, the third graph you get a horizontal line, but no matter what, okay, all these graphs are lines. So again, these are the linear functions, and so the first thing I want to do is I want to talk about the graphical behavior of these functions, because they all have some common characteristics. Okay, so one thing all lines have in common is that they are either increasing or decreasing. Okay, they are either increasing or decreasing, but they won't do both at the same time. Okay, so look at graph H right here. We talked about this a little bit in the last video. As you move from left to right, what's happening to y? Well, your y values are increasing. Okay, as we move from left to right, y values are increasing. So graph H, we would say, is an increasing graph. Graph G, on the other hand, as you move from left to right, y is decreasing. Okay, you can imagine this as being a downhill graph. So we call this a decreasing graph. And the one exception to that rule for lines would be horizontal lines, because horizontal lines actually are neither increasing or decreasing. So with the exception of horizontal lines, all lines are either increasing or decreasing. You may want to make a note that horizontal are going to do neither, though. Okay, in terms of maximums and minimums, lines will never have a maximum or a minimum, okay, because they keep going on forever and ever. So there's no high or low point on a line because they keep going. And of course, if we're deciding between a curve and a line would be a line. Last thing I want to look at is how you tell an equation is a linear function just by looking at the equation, not going through and graphing it. And so up here in the definition, I'm telling you that the family of linear functions includes functions of this form. F of x equals mx plus b, where m and b are real numbers. Okay, so in an equation, m and b would both be actual numbers. And so you could come up with several different examples to fit this form right here. You see three down below here. You see f of x equals x, and if I wanted to make this equation fit that
form up there, f of x equals mx plus b, I could rewrite this as f of x equals 1x plus 0. That would be the same thing as f of x equals x. So this fits in with that form up here. Okay, f of x equals negative 2/3 x plus 5 fits in with that form. If we replace m with a negative 2/3 and b with a positive 5, okay, then we get that same form. And then so does f of x equals 2. I could rewrite this as f of x equals 0x plus 2, and that would be the same thing as f of x equals 2, and that also fits that mx plus b form. Okay, so any equation that fits this form up here is going to give you a linear function. The easiest thing to remember about this is this form here does not contain exponents. Okay, so this form here does not contain exponents, unlike a few of the forms that we're going to see down below. So this is our family of linear functions. The next page, we're going to talk about the quadratic functions, and so here are the 4 graphs you should have had for your quadratics. F of x equals x squared matches with graph K. F of x equals negative 1/2 x squared plus 2x matches with graph M. F of x equals negative 3x squared plus 4 matches with graph P. And then finally the last one, f of x equals x squared plus 8x plus 12 matches with graph O. And so one thing you notice about all of these graphs here is they're all that U shape that we saw in the last video. That U shape has a special name. Its name is a parabola, and we'll talk a lot more about that in a unit that we do at the end of the year. But for right now, I just want you to know that U-shaped graphs are in the family of quadratic functions. And so let's talk about their graphical behavior first of all. So a quadratic function is going to be both increasing and decreasing. Okay, all quadratics are going to increase and decrease both. They are going to have either a maximum or a minimum, but not both. And all quadratics are going to be curves, okay, as opposed to lines. So let's look down at these 4 graphs here and talk about those characteristics. So this quadratic right here, it starts out, if you go from left to right, it starts out as decreasing. And then it gets to this bottom point right here. This would be the low point on the graph, or the minimum value. And then once you pass that point, going left to right, it starts increasing. So this one we would say is decreasing, then increasing. Okay, your next graph here does the opposite. It increases first from left to right. Okay, so as we move this way, we're increasing. Then we get to this point right here, which is the maximum point on the graph because it's the highest point. And then once we pass that point, we start decreasing again. So this would be increasing, then decreasing. Okay, and you can see the same things for P and for O. P, we're increasing first, then we get to a maximum, and then we start decreasing. So increasing, then decreasing. And then O, going left to right, we're decreasing, we get to a minimum point, and then we begin increasing. So now looking at the equation, f of x equals ax squared plus bx plus c is the form that you're going to fit all of your quadratics into. Okay, a, b, and c are going to be actual numbers. So if you look down here, you can see several examples of that form. Okay, the big thing to look for when you're looking for quadratics is you're looking for an x squared. Okay, anytime you see an equation that has an x squared in it, that is going to make it a quadratic equation. Okay, as long as that is the highest exponent. Okay, so x squared will be a quadratic equation. Moving on to the next page. The next page we have our exponential functions. These are the 3 exponential functions. F of x equals 3 to the x power should match with graph F. F of x equals 1/2 to the x power minus 5 matches with graph R. And then finally, f of x equals negative 1/2 to the x power matches with graph I. And so you notice all of these graphs have that sort of a L or a J shape, okay? And so they kind of either start out as a flat line and then look sort of like a vertical line, or vice versa. They might start out really, really steep, looking almost like a vertical line, and then they might look almost like a flat line. The one thing you want to keep in mind, though, is that these actually are not lines. They're curves. They're just curves that are either very, very steep or very, very flat at the far ends of them. Okay, so these are curves. Exponential functions are going to behave like lines, though, because they are going to be either increasing or decreasing, but they won't do both. Okay, so unlike quadratics, exponentials only do one thing, either increase or decrease, and exponential functions do not have a maximum or a minimum. So they're very much like lines, except for the fact that they're curves, of course. So if we look down here at function f, okay, if we go from left to right, we can see that the y values eventually start increasing very rapidly. Okay, they start going up. So this would be an increasing function right here. Graph R, if we go from left to right, we can see that the y values are decreasing. And then finally, graph I, if we go from left to right, we can see that the y values are increasing at first, and then they get kind of flat, but this would still be an increasing graph. Okay, the form for an exponential equation is going to be this form, f of x equals a times b to the x power. And the big thing to look for to know if you have an exponential is this part right here. If you have an exponent of x, then you have an exponential. Okay, an exponent of x will give you an exponential. Okay, the next family that we're going to look at is the family of absolute value functions. And so your absolute value graphs are going to be the following. F of x equals the absolute value of x is going to be graph B. F of x equals negative the absolute value of x is graph Q. F of x equals negative 2 times the absolute value of x plus 2 plus 4 is graph J. And then finally, f of x equals absolute value of x minus 3 minus 2 is graph E. One thing you may notice about all of these graphs is they're all V's. Okay, so all of your V-shaped graphs are going to be in the absolute value functions family. So the behavior of these functions is going to be very similar to your quadratics. They're going to be both increasing and decreasing. They will have either a max or a minimum. The only difference between these and your quadratics is that these graphs are not curves, they are made up of lines. Okay, so let's go ahead and let's take a look at these graphs in a little bit more detail. Graph B here, okay, this graph here has a minimum, it has a low point, and if we go from left to right, it starts out by decreasing, because the y values are getting smaller, and then as soon as you hit the minimum and start going left to right, it begins increasing. So this one we would say is decreasing, then increasing. Graph Q, on the other hand, it has a high point, so it has a maximum. If you go from left to right, it starts out as increasing, and then it decreases. So this one would be increasing, then decreasing, but again, it does do both. Graph J also has a maximum. This one begins by increasing, and then it begins decreasing. And then finally, graph E, this one has a minimum. It starts out by decreasing, and then it begins increasing. Okay, to figure out whether or not an equation is an absolute value equation is very, very simple. If you look at this, this is the general form. F of x equals a times the absolute value of x plus b plus c. And the easy way to figure that out is if you have absolute value bars and those absolute value bars contain an x, then that means you have an absolute value function. Okay, so you're looking for absolute value bars, and you need to have your variable, typically your x, inside those absolute value bars. Okay, we have two more families to look at now. The next family is our family of cubic functions. And we have three graphs that go with this. F of x equals x cubed, or x to the third power, is graph S. F of x equals negative 2x cubed minus 4 is graph L. And then finally, f of x equals 1/2 x cubed plus x squared minus x plus 5 is graph D. You'll notice that these graphs here have that sort of an S shape to them. And so let's talk about the graphical behavior. Okay, so cubic functions are interesting because when you talk about a cubic function, overall it is either increasing or decreasing. But if you look at the middle part, it's going to be a little bit different. So we're going to take a look at some examples. Those different examples down below here in just a second. Also, in terms of maximums or minimums, there really is no low or high point for a cubic function, okay, but it is going to be a little bit different in the middle. Okay, so the middle parts of cubic functions are going to behave a little bit differently than the overall function. And then, of course, cubic functions are curves as opposed to lines. So I want to look down at these graphs and tell you what I mean by that middle part right there. So again, it's different in the middle for cubic functions. So first of all, let's talk about the increasing and decreasing factor. So for graph S, overall this graph is increasing, we would say, okay, because from left to right, y is increasing, and then y keeps increasing as we go in here forever and ever, okay? But here for a while in this part, and this is kind of hard to see because it looks almost like a flat line, y actually begins decreasing for a little bit, okay? So overall, we would say that this graph is increasing because overall all y gets larger, but for a while it gets a little bit smaller here in the middle. Okay, it's easier to see that in graph D. Overall, this graph is also increasing because y is increasing here to here and here to here, but this part right here in the middle, you can see that y is decreasing. Okay, so that's what I'm talking about. The overall factor, it's doing one or the other, but there in the middle, it does the opposite. Okay, I also want to talk about the max and the mins. There is no low or high point on this graph because it keeps going down forever this way and up forever this way. But in terms of the middle, there is a maximum and a minimum for just that middle part right there. Okay, and that's what we call local max and local minimums. Okay, so that means that they're not the high or low points on the overall graph, but they are low or high points on just a small section of the graph. Okay, so again, these are called local max and local minimum points. Okay, and then so let's take a look at the equations for cubic functions. Cubic functions, this is going to be very similar to quadratics. Okay, so this is the long string of letters and exponents for a cubic function here. The big thing to look out for cubic functions is an x cubed, or an x to the third power. Anytime you have an x cubed, you know you have a cubic function. Okay, and finally, our last function family would be the square root functions. These three functions, you should have had graph t for f of x equals square root of x, graph n for f of x equals square root of x plus 3, and finally, graph a goes with f of x equals 2 times the square root of x minus 4. You'll notice that these graphs are each curves. Okay, so square root functions are curves. In terms of increasing or decreasing, even though all the ones I've shown you are increasing, they can actually do either. Okay, so there are examples of decreasing graphs as well. And in terms of a maximum or a minimum, they will have either one or the other, a maximum or a minimum. Okay, so each of these graphs here is increasing because the y value gets larger as you go left to right. You could also have a square root function that looks like this, and that has this shape right here. So that would be an example of a decreasing function. Each of these graphs has a minimum as well. Okay, this is the lowest point on graph A. Okay, this right here is the lowest point on graph N. If you had a graph that was shaped like this, decreasing, this would be an example of a maximum right here. So they have either a maximum or a min, and of course they're all curves. The way you tell whether an equation is a square root function or not is pretty simple. If you have a square root in the equation and that square root has an x inside it, then you have to be a square root function. Okay, so again, this video was just getting you an idea of how to match graphs and equations into their different function families based on characteristics. So I want you to be comfortable with knowing if I give you a graph, what family it belongs to, okay, based on what the shape is, and also if I give you an equation, what family it belongs to based on whether or not it has an x squared in it, a square root, absolute value, that sort of thing. Okay, so feel free to go back and rewatch anything in this video that you need to, and until next time, have a nice day. You're all wonderful people. Take care.